Let's see 2.4 exact equations. Level core. Let's see. Let me introduce level core. Okay. So um, probably you know about this one, level core. If you studied vector calculus, level core of function. That function is a function with a multivariable, right? So x and y. This is the set of all points x comma y such that f of x comma y is equal to constant, which means that let's say graph of that function with a multivariable like this surface, right? And then we collect the all points whose z coordinate is identical. Okay, so for example, maybe you know I don't know, maybe like this. Maybe like this. Okay. So all the points on this chord, their z coordinates are identical. Okay, this is called the level chord. Okay. So then the expression of the level chord is this f of x comma y is equal to c. Okay. C is the actually z coordinate. Okay. So here's the example. So x squared plus y squared is 1. So considering the left-hand side is a function with the two variable x and y, then that's the equation. I mean, um, this one is the expression of level chord whose z coordinate fixed to 1. Okay, so like this here. So then here I'm gonna take a derivative of this level chord equation of level chord. It's called the that's called the total differential or total differentiation. Okay, so total differentiation of f denoted by df. Okay, f is level chord, by the way. So then take a derivative is this partial f partial x. The partial is this is not the because f is not a function with a single variable. F is the function with a multivariable. So we have to apply the partial derivative. Okay, so partial and partial x dx plus partial and partial y dy equals a derivative thing. Because derivative of constant is 0, right? So derivative constant is 0. So the right hand side is just turns out to be 0. Okay. So right here, applying this one to the example x squared plus y squared is 1, then partial f, now partial x is going to be when you take a derivative f with respect to x, then that's a partial derivative, right? Then we need to we're going to consider all other variable as constant. So derivative x squared with respect to x is going to be 2x. And then derivative of y squared with respect to x is going to be 0. So we're going to get 2x. And the partial f and the partial y is going to be similarly, derivative x squared with respect to y is 0. And the derivative y squared with respect to y is a 2y. So the total differentiation of f in this example is going to be 2x and then dx plus the 2y and a dy is equal to 0. Okay. Right. So then then normally we want to find that dy, right? dy and then dx, okay, is equal to yeah, minus a second here, minus x over y, right? Over y. Anyway, so that's the total differentiation. By the way, this one. Okay, this is the total differentiation of f of this example. So let's say partial and partial x is m of x comma y, and the partial and partial y is n of x comma y. So here m gonna be partial and partial x, and then n is a partial and partial y. Okay. So this is called the exact differential equation. If for a given differential equation, the form of the differential equation has uh the exactly matched with this one, that is called the exact differential equation. So um so what? If this is the exact differential equation, what's the solution? F, right? Why? Because this one comes from what? Derivative of f. Derivative of f is equal to 0. So when you take an integral, then we're going to get f, the level curve. We're going to get this one. So, okay. So, okay, you got the exact differential. Once you figured out, okay, differential equation is exact differential equation. What's the answer? F. Okay, but the thing is that we do not know f, actually. That's a problem, okay? So this is the example, by the way. So we're gonna find, we'll start the journey to figure out how to find out f. Okay. So here's the example. dy dx is equal to this. Okay, well, this looks complicated. Definitely non-linear, right? First order, non-linear, right? Okay, probably this is separable. I don't think so. We cannot separate a function of x and function of y. So the separable? No. Okay. Is it linear? No, that definitely is not linear because of y square right there. Even we cannot, the factor out, the square, so it's not linear. Is it exact? Oh, how can you figure out, whether or not this is exact? Here's a idea. Okay. What was m? M is what? Positive x, right? So when you take the derivative, m with respect to y must be equal to the partial derivative n with respect to x, because n is positive y, So positive x, I mean, the positive x is going to be m. This is n, right? Then positive and positive y are going to be what? Positive x and the positive y. And the positive x, the positive n and the positive n is going to be positive f, y, and x. So you see that? Two guys is identical, right? So if you want to figure out if the given differential equation is exact, what you have to do is to find out m and n first. What is m? What is n? And then take a partial derivative n with respect to y and the partial derivative n with respect to x. If two guys are identical, I mean, then that equation must be exact. So here's the example. So going back to this example, all right, so we need to rewrite this one as this form. Something dx plus something dy equals 0. So we want to get 0 on the right-hand side, and then rewriting, doing something to get that kind of form. What are you going to do? Yeah, first one, dy dx. I need to move dx to the right-hand side. Okay. And then I need to move, the bottom one, the numerator denominator to the left-hand side. So 2x squared y dy equals minus, this. Okay, and then move this guy to the left-hand side to get 0 on the right-hand side. So, okay. Oh, yeah, I think this is matched with this one, the form of the total differentiation of the level curve. So that must be m, that must be n. Now we take partial derivative m with respect to y and the partial derivative n with respect to x. This is 4xy. This is 4xy. Okay. Oh, equal, right? That's why this is exact. Okay. So let's see. Yeah, so let me just, summarize what we did for figuring out if given differential equation is exact. Here's the theorems. Okay. So let's see. Suppose the first partial derivative of m x comma y and n x comma y are continuous in a rectangle R. So rectangle R means just the domain of the unknown solution of partial differential equations. Okay, because we want to find out the solution of the exact differential equations. We know the exact solution to the exact differential equation is the level curve f, right, of x comma y. What's the domain of f? Domain of this one must be lie on the xy plane. Because this is a function with the two variable x and y. So domain of this guy must be lie on the xy plane. And then the what? So so that's what we assume, that the rectangle, which is kind of maybe right here, that should be on the xy. Okay, must be right here. That's actually just domain. So we assume that the partial derivative, first partial derivative of m and n are continuous on that domain. Okay. Right. What does that mean? Because m and n are partial derivatives of f, right? So that means f is also continuous on this in the domain. Okay. All right. So that's the meaning of the rectangle R, which means the domain of the unknown function, exact differential equation, which is f. Okay, and then the first partial derivative m and n are continuous. That means f is also continuous. And then if the first partial derivative m and n are not continuous, then we cannot guarantee that these two guys are equal. This is a partial f with respect to x first, and then take a derivative with respect to y second. This is y first, x first. The very bottom, the assumption, big assumption for that, two guys are identical, two guys must be this guy, these two guys must be continuous. If a function is not continuous, then we cannot change the order of derivative. That's why they assume this. First partial derivative m and n are continuous. So this is an exact equation if and only if, this guy is equal to this. Okay, for every single point, for all points in that domain. Okay. So yep. Okay. You got it? Any questions, you guys? No. Okay, let me prove the theorems. Okay. So that exact equation is exact equation. If this is exact equation, then partial and partial y equals partial and partial x. And then if partial and partial y equals partial and partial x, then the equation is exact. So we need to prove the both ways. Okay. So let me prove that way. If the equation is an exact, then by definition of the exact equation, partial and partial x equals m, right? The partial f partial y equals n. Since their partial derivatives are continuous by hypothesis, because here we assume that first partial derivative of m and n are continuous, right? So that's assumption. Right? So we take the partial derivative, this guy, partial derivative of this guy with respect y, and then with respect x of this guy. Then these two guys must be equal. Proof is done. Right? So we assume that this is big assumptions, hypothesis. And then we assume that this is exact. So by definition of the exact, this must be m, this must be n. Right? And this, because of that assumption, you know, the partial derivative of m with respect to y must be equal to the partial derivative of x. The partial derivative of this guy with respect to x must be equal, must be identical. So, okay, and let me prove the other way. Assume that partial and partial y equals partial and partial x. So then we'll construct the, what we're going to do? We need to show that what? This is exact. How can you show that this is exact? M must be what? Partial and partial x, n must be partial f partial y, which means that we need to find out f. To show that this is exact, we need to find out f. And then partial f partial x equals m, and the partial f partial y equals n. So pretty much we need to construct the f to prove that this way. From here, we can get idea how to construct the f. That's why we need to prove that theorems. So assume that partial and partial y equals partial and partial x. That's the assumption, right? Okay. And then now let's construct the f such that partial and partial x m and the partial and partial y m. Where that comes from? That comes from the definition of exact equation. That comes from definition of exact equation. Okay. Once we construct the f such that this is equal this is equal that. Okay, the proof is done, right? So then define f as like this. Integral of m plus g of y. Where that comes from? Because we need to construct the f satisfying these two, equation, right? So then we take an integral on both sides, and we got this. Keep in mind is we take an integral with respect to x, right? And then take integral with respect to x. What happens? Then we're gonna get constant integration left hand side, but that constant must be function of y. Because when you take an integral on both sides, then take an integral with respect to x, then g of y becomes 0 because this is function of y alone. Okay, that's why we got not c, just constant, but function of y. Okay, now what are you gonna do? The partial f. Oh, let's see. Now, since the partial equals n right here, so when did we construct the f like this? Then partial x is gonna be m, right? Okay, so this guy satisfies the first condition equation. Now we're going to do something to f this one so that this guy satisfies second condition. Okay. Now what are you gonna do? From here, we take an integral derivative of f with respect to y, both sides. The partial y is going to be partial derivative of this guy with respect to y, and this is going to be g prime, right? Here, prime means that with respect to y, derivative of g with respect to y. Okay. So then, this we got this one right here, and then we take the derivative with respect to x again, x on both sides. Okay. So then the left-hand side going to be this, the right-hand side going to be that, right here. And then now we can switch the order of partial derivative, right? Okay. How can I do this? Because that's why the big assumption, remember that? The m and, f is a C2 space, we can say m and n are first partial derivative, m and n are continuous. So we can switch the order of the partial derivative. Then the partial, what are you gonna do? We're gonna take a partial derivative of this guy with respect to x first. Keep in mind this is what? Function of y. Taking partial derivative with respect to x, this is gonna be 0. Right? And then now the take a derivative of this guy with respect to x, but this is integral with respect to x. Taking partial derivative with respect to x, they're gonna be canceled out. Okay, we cancel out, right? So we got m, and then partial derivative of m with respect to y, that is equal to what? This is equal to, yeah, the partial is equal to this. We got this one, right? Okay, right here. You see? Now then what? We assume that what? Give me a second. Partial M, oh yeah. So now this one must be equal to that partial M partial X, right? Because we assume that. We prove this way, right? We assume that partial M partial Y equals to partial M partial X. So this is equal to partial M partial X. Now we see partial X, partial X. Cancel them out. Then N is equal to what? This one. N is equal to, oh, give me a second, sorry. N is equal to this one, right? So partial and partial Y is N, sorry. So when you cancel that out, the partial derivative with respect to X and here, then we got this one. Partial and partial Y is equal to N. So we just show that F satisfies not only first condition, but also second condition too. So from here, we got the idea how to find out F. So from here, well, we got partial like this, right? Right here. Then we gotta take the integral. I mean, so give me a second. Oh yeah, here, right here. Sorry. So when you construct the F like this, then this guy satisfies both conditions, and then eventually F is the solution of that exact differential equation. Okay, so that's the main idea, how to find out its solution to exact equation. So here's a method for solving exact equation. Step 1, if m dx plus n dy equals 0 is not exact, stop. Apply the other method, okay? Separable, linear, okay? If it is, yeah, put f as the integral of m with respect x plus 3y. So here's the second things to do. Next thing is to do. So find out g1. Because the partial to find out, g1, we take take derivative, partial derivative f with respect y. Okay. Derivative of this guy with respect y. Okay, take a derivative of this guy with respect y. Okay, but this is equal n. Keep in mind this. M and n are given in problems. We know m and n. So this is equal n, right? So this is known, is equal to m is also known, right? So to find out y, we take integral. Since we know n, right? It's easy. Yeah, we can find out integral of n, right? So see, give me a second. Yeah, take integral. Okay. Give me a second. Yeah. Oh yeah. So we take integral. I'm sorry. We take integral of just g prime. Sorry. Take integral of g prime y with respect to y. Okay, not whole thing. Sorry, I made a mistake. Okay. So now then, solution to this guy is given implicitly by this. So normally in exact equation, the solution to be expressed as implicit form. Okay. Implicit form means that is the first is to against to explicit. Okay. Implicit means that the unknown function y cannot be expressed as the a function as a function of the dependent variable x, which means that you cannot isolate y. Okay. In that case, if y unknown function y can be expressed as the the independent variable, that means that is explicit. Okay. If you cannot isolate y, then that's going to be implicit. Okay, so which means that here's what is solution? Solution is y, okay, but we cannot isolate y normally in the solution to exact equation. Let's see example. This is the example. So 2xy minus secant squared dx plus x squared plus dy equals 0. This is a solution. Step 1. We need to see if this guy is an exact equation. So partial and partial y equals 2x. Yeah. Take a derivative with respect to y. Then you're going to get 2x in the first term. And the second term is there is no y. So this is going to be 0. Okay. And the partial and partial x is going to be 2x, right? Okay. So this is exact. And step 2, we set f as integral of m with respect x plus 0y. Okay. So what is m? 2xy minus secant squared plus 0y. So take the integral of this guy is going to be x squared plus x squared times y minus tangent. Integral anterderivative secant squared is tangent, right? Plus 0y right here. And then we take so what? We didn't use n, right? So because actually n is a positive y. So we take an integral derivative of f with respect to y. Okay. Because then x squared plus 2y, which is n, is equal to derivative of this guy with respect y. So we got x squared plus g prime y. See, x squared plus 2y is equal to x squared plus g prime y, which means that g prime y must be equal to 2y. So we take integral both sides, then g y is y squared plus c. Then step 4, yep. So finally we got this. F of x comma y is, yeah, we figured out. Okay, so what is c? C will be determined by initial conditions, okay? So we just plug in this one into 0y. And f is going to be x squared times y minus tangent squared x plus y squared plus c equals 0. Okay. This is how to do it.